Hello, my name is Preston Lewis, and for my sensor design project, I built a medical device that can detect the light intensity of the environment around it. For this medical device, I envision it being used in surgical procedures, specifically endoscopic procedures. As you can tell, my microcontroller or my nuclear board is providing a 3.3 power supply to my photoresistor and this 330 ohm resistor connected in series. These actually form a voltage divider, which will be used as the input voltage to my microcontroller at the A0 pin. As you can also see of this circuit, I have a simple LED circuit over here where an LED is connected in series with a 330 ohm resistor, powered by the analog output pin of my microcontroller, A3 pin. If you look at the code, you can tell that I've defined my A0 and A3 pin as my analog input and analog output pin. I then have three other variables, val in, vin, and vout, which will be used to read the ADC from the input pin, the voltage read from the input pin, and B, the voltage read from the output pin. I also use an infinite while loop, which will allow me to continuously update my input voltage. To better understand what my code is doing, I'll show you this block diagram. So essentially, my device is trying to optimize the light of the environment for surgical procedures. To do this, I'm using the relationship that my photoresistor will decrease in resistance when the light environment intensity increases. For your information, I've done the calculations, and at the brightness of around 600 lux, the input voltage will be around 1.49. And for a brightness of 1000 lux, the input voltage will be around 1.73. These conditional statements you see here, shown in these diamond shapes, will be used to control the LED to keep the environment brightness around 600 to 1000 lux. However, since an LED is not bright enough to actually control and change my photoresistor, I'll be using a flashlight in my testing. My circuit with this bike headlamp here. For my actual testing, I used my iPhone flashlight, which seemed to work a little better with the photoresistor, but I'll try and get to work here with this bike flashlight now. So essentially what we should expect is this LED is on currently, which means the environment is not bright enough to reach the optimal range. So when I shine my flashlight on it to increase the brightness of the environment, the LED is going to turn off in attempting to reduce the brightness to get it back to the 600 to 1000 lux range. As you can see, the LED is turning off, and when I remove it, the lighting is back to not being bright enough, and so it'll again light up. There is an optimal range, and I'll just attempt a couple tries to show it to you guys, but no promises. Maybe that's it. Maybe it's a little dimmer. Yeah, there we go. As you just saw, the LED paused at a mid brightness of not being maxed and not being off. This is the optimal range, somewhere between 600 and 1000 lux. And now I'd like to show you the results of my actual testing. And these are my testing results. As you can see, I had two actual tests, which I compared to a theoretical result, which I was able to get from determining the lumens of my flashlight. I then had these other two tests where I measured the lux values reported from the photoresistor, and I've determined that while they're not 100% accurate, they do measure in a pretty consistent relationship and were a great resource in this project or proof of concept. Thank you for watching my video, and I'd like to answer any questions.